So what we have here is an analysis of how reliable our measurement system is. And of course we would like to get the same measurement to infinite precision every time we take it, but noise creeps into everything we do. But hopefully one will not find a relationship when you're measuring the same thing time and time again. And so, but what we found is that when we were measuring silicon dioxide thickness, the measurement drifts over time when both light sources aren't used. And so that's not a good thing, and it's a problem to be solved. So what we did is we measured some data. We took a silicon dioxide film. The growth parameters are listed down here, and we calibrated the system and then just took the oxide thickness measurements in the same place 30 times. And in the analysis I just do measurement, but it is over time, and you can download this file and you can see what we get, right? And it gives us a mean, standard deviation, right? That might seem pretty good, right? But I actually did wafer number, but I could have done elapsed time, and perhaps I should have. Then you could see how things are drifting in time. But wafer measurement number is a proxy for time. So somebody could go and improve that. Anyway, we're using pandas again. We have some NumPy and plotting, and I'm going to use a linear regression differently, a different Python way. And you can see that I'm having a URL. I can read that in. I can get the variables. But in order to do some things with NumPy, I need to rename the variables to something like that's just one word with no special, well, just one word, right? Elapsed time, sample ID, they have spaces, and sometimes it just, you need to make better code words. So this will work for any Filmetrics file. Because the variable's at point 0, I'm going to call it measure in n. The variable at column 1, right, I'm going to call thickness. And then, oh, I even do have time. Anyway, I guess I could have done it. So, right, I'm just calling things, just using some panda type procedures to name data, get columns of data. That's all that's doing, right? Some of the legends I think are from a previous thing, so there isn't top, bottom in theory, and we have our plot, right? And so here's our silicon dioxide thickness. Yeah, and if you want to know how to do angstroms, just look right there. There's the code for angstroms. And you can see that, you know, by eye, it's drifting. But the noise actually is almost swamping out the relationship. But sometimes you just have to look at the data and see. All right. But we get our mean, standard deviation, which looks pretty tight, right? But still, there's a relationship over time that we don't like. Then so this is the code to do the linear regression in a different manner. It's the same algorithm, right? But you get kind of this plot rather than the Lindgress from SciPy. Not quite sure which one I like better yet. But anyway, here's R squared, 0.32, right? And you might think, oh, that's kind of low for a measurement. Well, in fact, what we really want is something like completely random. So I would like to see it near zero, right? So the fact that there is, like a significant R squared means there's a relationship or indicates. And then when we look at the constant and wafer, the constant is the offset and wafer would be the slope, right? And look at the p-values, they're less than 5%, and if you were using less than 1%, there's a significant relationship there. So sometimes you're looking for a relationship that, you eat this food and you lose this amount of weight, right? But we don't want a relationship in our measurement system. At least we haven't really done an experiment. But you can plot that line and then plot the data, right? And you can see the slope and the offset, right? So there's a relationship. So looking at it, right, you can look at it and see a downward trend, and then when you do a formal analysis, you can see there's a relationship. R squared is large, for what I would expect to a random thing, and the p-value is less than 5%, right? Now, it turns out that the white light source, our tungsten bulb, had died, and they're kind of expensive and they take a long time to come. And so we were just trying to get an idea of what a thickness was, and we were able to, right? That we know the ballpark, of that oxide thickness, right? And in the meantime, a new one was ordered and installed, and there's even now a spare next to the Filmetrics, and the issue has gone away, right? So yeah, I kind of knew, I didn't know, well actually I didn't know how good it was going to be until we did this analysis. So you'd say, well, problem solved. However, it does seem that the Filmetrics, right, uses white light and a UV source, and you need the UV source for small wavelengths so you can measure thinner films. So it could be that, yeah, in general the problem has solved, but if one were measuring very thin thicknesses, right, well, that's where the UV is really important, right? Those UV wavelengths shouldn't need to be accurately measured. So it could be that if I were to measure things smaller than 146 angstroms, we could have this problem, and one might have to calibrate, take maybe 5 measurements, and then recalibrate. Right? You have to be very careful with, the thinner you go. So, but for normally what we're doing in lab, the issues have gone away. But yeah, we could just, but one could look into, measuring a thinner film, or could this be improved by more frequent calibration? But when we do this on thicker films with both light sources working and also narrowing down the UV range, there is a UV range that does fluctuate wildly from measurement to measurement, and you can just kind of narrow in. Anyway, now when you do your work on a working system, you could use this file, right? And just plug your measurements, share your doc, and all you got to do is change the URL and then see what happens. And you should not have a relationship. Anyway, that's that.